Hello students, in our previous lecture we did the cantilever case with subjecting to point loads, and we also did the case in which the cantilever was subjected to uniformly distributed load at a different span of the beam. We are going to look at the case where we are going to have the combination of the loads on the cantilever. That means the cantilever beam is subjected to both point loads as well as the uniformly distributed load at the same time. So here you can see in this diagram that there is a beam which is ABCDEFF, and this is subjected to variety of loads. There are point loads acting at point A of 2 kilonewton, at point B it is of 2 kilonewton, at point C there is a load of 3 kilonewton here, and then at point E there is a load of 1 kilonewton. So these four are the point loads which are acting at different length from the fixed end, and we are also given that the beam is subjected to a uniformly distributed load of magnitude 2 kilonewton per meter between point B and point D. So from point B to point D it is subjected to a uniformly distributed load of magnitude 2 kilonewton per meter. The total length of the beam is 5 meter, and their exact distance of these loads where they are acting is also given to us, and we need to draw the shear force diagram and the bending moment diagram for this beam. Now, as we did in our last lecture, in the similar manner we will progress here. For the shear force diagram, we will first consider the span AB. So we'll start from the free end and consider that the beam is cut somewhere between A and B. So let's assume that the beam is cut here. So if we assume the beam to be cut here, and we draw the free body diagram of the right hand portion of this cut section, that means from the point where the beam is cut and to the point A, there is only one load that is acting, is 2 kilonewton load, external load that is being applied at point A. So the shear force will be developed in this section will be equal to the 2 kilonewton only, and the equation of this will be Fx is equal to 2 kilonewton. As this equation is not dependent on the value x, so we are going to get the value Fa as 2 kilonewton and Fb as 2 kilonewton. That means the shear force value at point A and point B, using this equation, we are going to get as 2 kilonewton at both the places. Now let's go ahead and consider the section BC. So if we assume now the beam to be cut somewhere here between point B and point C, let's say arbitrarily it is cut somewhere here, and we draw the free body diagram for the remaining portion of the beam, that means from point A to this point where the beam is assumed to be cut. So we see that there are 2 point loads, one is of 2 kilonewton, the another one is of also 2 kilonewton, they two are acting. So there will be resisting shear force of magnitude 2 plus 2 kilonewton because of these point loads that are acting on the beam. Apart from that, these two loads, we also know that there is a uniformly distributed load of 2 kilonewton per meter also acting. You see here this portion. So in this portion there is a uniformly distributed load of 2 kilonewton per meter is also acting on this body. So the magnitude of the force that is acting because of this uniformly distributed load will be equal to the UDL value, that means 2 kilonewton per meter, multiplied by the distance at which it is acting. So if we say that this is my x here, so from the free end, that means from point A to the point where the beam is assumed to be cut is distance x. So the distance at which this load is acting is nothing but x minus 1. So that's why in this shear force equation we will have this 2 kilonewton per meter value multiplied by the distance, that is x minus 1. So that gives the amount of load that is acting because of this UDL acting over this span. So the net sum will be 2 plus 2 plus 2 into x minus 1. So that becomes our equation for the shear force for the span BC. and we are going to evaluate this equation at the two extreme ends of this section BC. So we are going to put the value once x equal to 1 for the point B. So FB will come out to be 4 kilonewton if we substitute x equal to 1. If we substitute in this equation x equal to 2, the value of shear force at point C will be calculated as 6 kilonewton. Now let's apply the same logic, and let's keep on doing the same thing, and we assume the beam to be cut somewhere here between point C and D. So there will be a point load of 2 kilonewton to the right of it, another point load of 2 kilonewton, and then there is a third point load of 3 kilonewton. So that's why in your shear force equation there will be 2 plus 2 plus 3. These three terms are appearing here, and then there is a uniformly distributed load. This is the uniformly distributed load that is acting here in this area. So we need to multiply the uniformly distributed load value with the length for which it is being applied. So as now x is here, this total distance from A to this cut point, so the distance at which this uniformly distributed load is acting is x minus 1. So that's why you get 2 into x minus 1 here also in this equation. Now we will evaluate this equation for the two different ends of this section, means for the point C and point D. For point C, x is equal to 2, so that's why pardon me, this is FC here, this is FC. So FC value will be calculated as 9, and for point 3 the FD will be equal to 11. So by this equation we can calculate the value of shear force here. Now we go ahead and assume the beam to be cut between point D and point E. So here we are assuming the beam to be cut. Now the forces that are acting to the right of it are, one force is 2 kilonewton, another is 2 kilonewton, third one is the 3 kilonewton. These are the 3-point loads. So you get here 2 plus 2 plus 3, these three values in the shear force equation for this portion. Apart from that, we know that there is a uniformly distributed load from point B to point D. So that total distance at which it is acting is 1 plus 1, that is total 2 meters, and the magnitude of the load is 2 kilonewton per meter. So therefore the complete uniformly distributed load that is acting here will be applied. So there is a 2 kilonewton per meter multiplied by the distance over which it is acting, that is 2 meter. So that becomes 2 into 2. Now here we can calculate it for both the extreme ends, that is from point D and point E. This equation is not dependent on x. This is going to give us the same value, FD and FE both equal to 11, using this equation. Now the last portion, we can do the similar exercise and assume the beam to be cut here between E and F. Up to this point all these forces will be acting, that means 2 plus 2 plus 3 plus 1, these are the 4-point loads, and they are appearing here, 2 plus 2 plus 3 plus 1. Apart from that, there is a uniformly distributed load of 2 kilonewton per meter acting over a distance of 2 meter. So therefore you get a 2 into 2 here in this equation. The net result of this is going to give you the value if you substitute x equal to 4 or x equal to 5, but this is not dependent on x. So the total value that it will be evaluated for will be 12 kilonewton. Now we can plot the shear force diagram here, and as per our convention this shear force is turning out to be positive. So I'm not going to discuss it again. We have discussed the sign convention and other things in our previous lecture in detail. So just keep on drawing it on the positive side, that means above the axis. So first we start from the point A. At point A we have evaluated the value of FA is equal to D2. So we will choose certain scale and we plot the value 2 here. Then at FB it is 2. So from point A to B we are going to get a straight line. You see this equation is not dependent on x, so there will be a horizontal line that will be appearing with the change in x. So from point A to point B, you are going to get this horizontal line. That means from 2 to it's going to remain 2. As soon as you reaches to the point B, from the portion BC side, the FB value is given as 4. So there will be a rise of the shear force from 2 to 4 at point B. So you get it here as 4. So you will draw a vertical straight line here, and then for x equal to 2, this value is going to be 6. So there will be a ramp here. So you will have a straight line portion here connecting the point 4 for the shear force for the point B as 4 to shear force at point C as 6 kilonewton. So you will get a ramp here. Now after reaching here at point C, this is FC actually, I have written it FB, but this is actually FC. So for the value of FC changes from 6 to 9 here. So there will be again a vertical line here appearing at point C, so which shows there is a change in the shear force from point at C from 6 to 9, and then at point D it becomes 11. So again there is a ramp here. So you get here from 9 to 11. So there is a straight line increase here from point C to point D here. Further on at point D it remains 11. For point E it remains 11. So from point D to point E you are going to get a horizontal line because the values of the shear force at both the points are same. So you will get a straight line here, and when you evaluate it for the point for the section EF, you see there is a change in the shear force at point E from 11 to 12. So there is a vertical straight line going from 11 to 12, and then it remains constant up to the point F. So it remains 12. So this is the kind of a shear force diagram that we will obtain here. So we see there are straight lines appearing here in all this shear force diagram, but there are horizontal lines and there are inclined lines. So these inclined lines are appearing wherever there is a uniformly distributed load, which shows that there is a dependent on X because of this uniformly distributed load. So these ramps are appearing here, you see in this portion and this portion. At elsewhere we are going to get the horizontal lines only in this diagram. Now we will go and calculate the bending moment diagram, and we'll start again the section wise. Let's start with the section AB. So bending moment is nothing but the force that is being applied multiplied by the distance from the portion where we assume the beam to be cut. So for the portion AB, we assume the beam to be, let's say, cut here, which is at a distance x from the point A. The force that is acting is 2 kilonewtons. So 2 into x, that is your shear force that you obtain here. You substitute value of x equal to 0. So you get the value of bending moment at point A as 0. And when you substitute x equal to 1, you get the value of bending moment at point B as 2. Now when we assume the beam to be cut at somewhere between B and C, so like if the beam is cut somewhere here between B and C, so there are two forces, point loads of 2 kilonewton each. We need to multiply them with their corresponding distances. The first force that is acting at point A here is at a distance x from the cut section, so there will be 2 into x that is appearing here. The another 2 kilonewton point load that is acting will be acting from this cut section as at a distance of x minus 1. So here we are talking about here we are talking about the distance from of this load from this cut section here, as this distance from the free end of this beam is x. So the distance that is in question is this, where the load is acting, 2 kilonewton load is acting at x minus 1 distance from this cut section. So therefore you get a value of 2 into x minus 1 here in this equation. So this is what you are getting here. So there is 2 into x minus 1, that is because of the point load that is acting here. Now apart from these, we also have here the uniformly distributed load acting. So you see this small portion that we have here is a uniformly distributed load, And as I have told you in the previous lecture also, for the uniformly distributed load, we can assume this load as a kind of a point load, and we can assume it to be acting at the middle of the length for which it is acting. So as it is acting for a distance of x minus 1 distance, so we can assume that it is acting at half of it. We can take it as a kind of a point load. So let's say this is cut here, so I can see it is acting somewhere at the middle of point B and point here, this point here. Okay, let me just enlarge the view for you. So here we have this diagram, and we assume the beam to be cut here, and this is the amount of uniformly distributed load that is acting in the beam. So we can assume that it is acting exactly at the middle of it, somewhere here. So as this distance from here to here is x, and this portion is only x minus 1, so we can assume that it is acting at x minus 1 divided by 2. That is the distance over which it is acting. So therefore you will get the term, the 2 multiplied by x minus 1 into x minus 1 by 2. So you get the 2 into x minus 1 whole square by 2. So this term will appear here in our bending moment equation. Now we will evaluate this equation at both the ends of the beam, this portion BC. So when x equal to 1 we substitute here, we are going to get the value of bending moment at point B as 2, which is same as we obtained in our previous case. This is the kind of a check also you can apply and see the value of the bending moment for both the portion of the beam obtained from the point A, let's say from the AB and BC. It should come out to be the same. If there is a difference between them, then there should be some kind of error in your next equation that you have obtained. Now if you substitute x equal to 2, you will get the bending moment value as MC equal to 7. So between point 2 and 7, this variation will be quadratic or the parabolic. You can see there is a quadratic term appearing, so it is showing that the distance the value of the bending moment will be varying in a parabolic fashion here between these 2 points. Now we will calculate the bending moment for the portion CD. The same logic will apply over there also. So you will get the first 2 terms will be the same as here, 2x and 2x minus 1. Even in fact this term, because of the acting because of the uniformly distributed load, will also be the same. So apart from these 3 things, there is another new load that has appeared, is 3 kilonewton, which shall be acting at a distance of x minus 2 from the cut section. So you will get 3 into x minus 2 here appearing in this equation. You are going to substitute x equal to 2 and x equal to 3, the 2 extreme ends of the section CD. So you will obtain the value of bending moment as 7 and 17 here in this equation. The last section that remains is the section, not the last section, but the next section that remains is the section D. If you assume the beam to be cut somewhere here between D and E, of course there will be 2x term, 2x minus 1 term, and 3 into x minus 2 terms. These all 3 terms will be same. But now you can take this whole uniformly distributed load to be acting at the middle of this span. So if you look at here, so this entire uniformly distributed load, which is acting for a distance of 2 meter, you can assume to be acting at exactly at the middle. So this value, the distance of it from the cut section will be x minus 2, and the value of this is 2 kilonewton per meter multiplied by 2 meter distance over which it is acting. So therefore you will get the value of 2 into 2, that is the 4 here, that is appearing here. This is 2 kilonewton per meter, and the length over which it is acting is 2 meters, so that's why 2 into 2, that's a 4, and it is acting at a distance of x minus 2 meter from the cut section, so that's why you get a distance of x minus 2 here. Now in this equation, if we substitute x equal to 3 and x equal to 4, we will obtain the value of bending moment at point D and point E respectively. You can keep on applying it and obtain the equation for the section EF also, which will be straightforward, and I leave it to you as a exercise to be carried out by yourself. Now let's go on and plot the value of bending moments that we have obtained from this equation. So this is straightforward. For point A it is 0, so we start from the 0, and you see this is making a drooping shape, and we have assumed that drooping shape to be having the negative notation, so we'll plot all of these equations on the negative side. So I have not put a negative sign here on this equation, but as when we are going to plot them, we are going to plot them below the axis. So let's start from the 0, ma equal to 0, then we have mb equal to 2, so we got a 2 value here. Between 0 and 2 there is a straight line linear change in the bending moment, so you will get a straight line here, and then you go and see that MC is 7, and between point B and C, as you are getting a quadratic relation, so you will get a variation, a parabolic variation. So here the value is 2, here the value is 7, but in between this point B and C there will be a parabolic variation. It's not a straight line, just mind it. And then from point C to D there will be change from 7 to 17. You get a MC equal to 7 and MD equal to 17. Again there will be a parabolic variation because of the term of quadratic nature appearing here. So from 7 to 17 again you have a parabolic variation. Then from point D to point E, it is the values are changing from 17 to 28. So here the equation is linear in x, so you will get a straight line. This portion between 17 to 28 is a straight line, and if you calculate the equation for the last span, that is for the span EF, you will find that the MF, the value of bending moment at F, is turning out to be 40. Again there will be a linear relationship, so there is a straight line with a different slope appearing here. So in this way we can draw the shear force and bending moment diagram for the cantilever beam, which is subjected to point loads as well as the uniformly distributed loads. Now we can see some other cases also of the beams. The first amongst them is the simply supported beam, which is subjected to point load at center. So you can see this is the simply supported beam. When we discussed about the variety type of beams, I told you about the cantilever beam, also about the simply supported beam. You can go and review those lectures again if you are not able to recall that. So this is simply supported beam supported at point A and point B. There is a point load acting exactly at the middle of this beam of the magnitude W. So the total length of the beam is small l, and the load is acting exactly at the middle from both the ends, so it is a distance of L by 2 from both the ends, which is shown here. Now because of the application of load W, there will be a vertical reaction of the support. So those reactions are given by the RA and RB. So at point A and point B, because the beam is supported at these 2 points, there will be vertical reaction at both these points of magnitude RA and RB. The first thing that we need to do in the case of simply supported beam is to find the reactions, because from wherever we start, either from the left end or right end of the beam, if we don't know the reactions value, we cannot draw the shear force diagram. So let's start with the obtaining the reactions. In this case the obtaining reaction is straightforward because the load is exactly acting at the middle of it. That's the only load that is acting on the beam. So the reactions RA plus RB will be equal to W, and they are acting at the same distance. So the total net magnitude of this reactions will be exactly equal to half of it, the applied load W by 2. So I'm not telling you the that you should go and find the moment in this case. Now once we have obtained the reactions at point A and B, which is equal to W by 2, let's draw the shear force diagram. So for drawing the shear force diagram, let's assume the beam to be cut somewhere at the middle of the beam. So like you see here, the beam is assumed to be cut here between C and B. So let's see that it is cut at somewhere section E dash E dash. Now I will draw this diagram here. We started in this equation, in this problem I have started with the left hand side portion. It doesn't matter, we can start from the right hand side also, but let's first take this case where we are talking the section AC and the beam is assumed to be cut at, let's say, D dash D dash. So if we assume the beam to be cut here at this D dash D dash, if I draw the free body diagram for this portion separately, I see there is only one force that is acting here, that is the reaction force at point A, RA. Apart from that, there is no other load that is acting. Now to balance this reaction force RA, which is acting in the upward direction, there should be a shear force of equal magnitude acting in the downward direction at the cut section D dash D dash. So my shear force value will be Fx will be exactly equal to RA, and as I have obtained RA is equal to W by 2, so it should be equal to W by 2. And because of the sign convention, we have chosen this kind of a shear force situation will give us to the positive sign, and we will draw it on the positive side of axis. And similarly, we can go and do the exercise of assuming the beam to be cut at the next section CB at, let's say, E dash section. If you draw the phoeboid diagram here, so you see there is a force of RA magnitude acting in upward direction, there is a force of W external force acting in the downward direction. So net shear force that will be produced in the section E dash will be equal to the algebraic sum of these two forces, that means RA minus W. So my shear force equation will be RA minus W. I substitute RA equal to W by 2, so this will give me Fx equal to minus W by 2 this time. So my shear force will be changing from W by 2 to minus W by 2 at the point C, okay, and it will remain as minus W by 2 at the other end also. I can draw the shear force diagram, and you see here at point A it is W by 2, at point C it is W by 2. Then for the next section CB, if I evaluate the Fx equation, it will be changing from W by 2 to minus W by 2 at point C, and then it goes and make a horizontal line up to point B and giving you the same value of minus W by 2. So you are going to get these two rectangles, one on the positive side and another one on the negative side of the axis. Now the bending moment diagram, again, if you look at this figure here, so we see this reaction force is acting at a distance x from the cut section. So this will give us the bending moment as force into distance is equal to RA into x. So this will give us this equation here, which I have written over here, RA into x. So RA value is W by 2, so the equation becomes W by 2 into x. If you evaluate it at x equal to 0, this will be MA will be 0, and for x equal to L by 2, this is going to give you value WL by 4. Now for the other end, for the section CB, if I look at this equation, there is a force of magnitude RA acting, the reaction force, and there is the external force W acting. And for the cut section E dash here, the distance of RA is x, while the distance of W is x minus L by 2, because this distance is L by 2, okay. So the distance of W from this cut section will be x minus L by 2. So there will be a bending moment of magnitude RA into x, and which is acting in a clockwise fashion, while there is a bending moment due to applied load W acting in the opposite direction, that is anti-clockwise direction, and its magnitude will be W into x minus L by 2. So RA x minus W into x minus L by 2 is our bending moment equation, which we will evaluate for x equal to L by 2 to obtain the value of bending moment at point C as WL by 4, which is same as we obtained from the previous equation. And if I substitute x equal to L, my bending moment at point B will be 0, and we can plot it here. So it is 0 at point A and point B, while at point C the value becomes WL by 4, and it is straight line here. So you are getting these straight lines because of we have the straight line relation in our equation for the bending moment. So it is changing from 0 to WL by 4 in a straight line manner. You get, say, kind of a ramp here, ramp up and ramp down. So in this way we can calculate the shear force and bending moment for a simply supported beam which is subjected to point load. In the coming classes we will do some more cases of the simply supported beam.